Vijit, for inviting me here and to deliver this talk. This is my third time to TIFR in this seminar series, Quantum Space-Time, and I'm very happy to be here for the third time. It's a very nice place. Okay, so I'm going to speak on this topic, new multiplets in n equal to 2 conformal supergravity. So this is basically based on a couple of this work done with the first one with Daniel Butter, Subramania Hegde, and Ivano Lodato, and second one with Subramania and Ivano. So, okay, so the plan of my talk is the following. So I will start with a brief review of what is a superconformal gravity, and I will start with the basic thing of understanding conformal gravity as a gauge theory, and then how we can extend it to conformal supergravity. And in particular, we will discuss about Weyl multiplets of 4-dimensional conformal supergravity. These are one of the important ingredients that goes into the construction of conformal supergravity. And then I will briefly review about the Weyl multiplets in 5 and 6 dimensions. I will not go into the details. I will basically tell what are the things that I want to focus on from the results of Weyl multiplets in 5 and 6 dimensions. And then I will tell one of our results, which is this n equal to 2 dilaton Weyl multiplet. So this is a different kind of Weyl multiplet that we won't be discussing here. This is different from the Weyl multiplets that I would have here, and that's called the dilaton Weyl multiplet. And that's basically motivated from the construction of Weyl multiplets in 5 and 6 dimensions. And then I'll tell you how we constructed this dilaton Weyl multiplet in 4 dimensions. And then I'll tell you about a different matter multiplet in n equal to 2 conformal supergravity, which we call a real scalar multiplet. Right? It contains a real scalar field with a non-vanishing Weyl weight. I will discuss about that, and then I will end with some future directions. Okay, so yeah, so this is roughly the plan of my talk. I will see how much I can get into the last part. How much time I have. Yeah, so we'll see. So, okay, so let us start with conformal gravity as a gauge theory. So what is so what we do is basically, you start with writing down a gauge theory based on the conformal algebra. So it's a non-abelian gauge theory because conformal algebra is a non-abelian algebra. So just like you construct any non-abelian gauge theory corresponding to each generator, you write down a gauge field and its associated field strength. So the generators of conformal algebra are the translation, Lorentz transformation, dilatation, and special conformal transformation. So corresponding to each generator, you have a gauge field and its associated field strength. Okay. So, but so far it's just a gauge theory. I mean, you can from the structure constants, you can write down how the gauge fields transform, how the field strength transforms, and so on. Okay. But that's just a gauge theory. But how to go from here, from this gauge theory to the theory of gravity. So what you need to do is you need to impose constraints so that local translations is realized as diffeomorphism. Okay? Because in a theory of gravity, you don't have a translation symmetry. Rather, it has to be replaced by a diffeomorphism symmetry. And that can be achieved by imposing certain constraints on the field strength. And then, yes. Yes.
I thought, so like in 3 dimensions, the way gravity becomes a gauge theory, because you take the turbine and the spring connections, E plus omega.
Right.
And the reason why this works is because E and omega
both have the same 3
degrees
degrees of freedom. Exactly.
Now here in 4 dimensions,
it is
E will have 4 degrees
exactly.
of freedom and
Yeah.
omega will have 6.
Yeah. So here you are not, unlike 3 dimensions where you rightly said that you have a theory of gravity and you realize it as a gauge theory, like SL2R cross SL2R gauge theory, by writing the combination of E and omega as a left SL2R and the other combination as a right SL2R. Right, where diffeomorphism is a part of the gauge, like the SL2R plus SL2R gauge symmetry there. But here it is not like that. Here you start from a gauge theory, and then you convert it into a theory of gravity by imposing these constraints. Like like what you're talking in 3 dimensions is a first order formulation where you don't impose this constraint. Right, you're treating your E and omega as independent gauge field, and then you take this. Yes, right. So it's more like the second order formulation where you're imposing this constraint to which will basically determine your spin connection omega in terms of E as a dependent gauge field. And right,
Yeah.
yeah,
That's what it is.
yeah, yeah.
Also, all the currents in conformal symmetry,
Huh.
they are not independent, right? They come out of stress tensor. You contract the stress tensor with various spinning vectors to get various currents
Huh.
associated to
Huh.
all these translations, special conformal form.
Yeah.
So how can it be that the gauge fields associated to them can be independent themselves? The gauge field, the
Huh.
previous part,
Huh. Okay, right,
you have this gauge field
Huh.
for each and every one of them.
right.
But
So,
you know the current, for example, the
Huh.
P comes from just the stress tensor. The D is essentially X times stress tensor.
exactly. So you don't, yeah, right. So, yeah. So basically, like, so if you are taking a supersymmetric field theory with certain symmetry, like you'll have a translation symmetry, so it will have a stress tensor, energy momentum tensor, and that will couple to the graviton, which is a linearized metric, and so on. Yeah. Whereas you will not, yeah, you will not, I think, have.
Current for rotation essentially,
Huh. It will xt type of thing. So it's not an independent current, right?
Yeah.
So the current for M is not an independent current, right? So you will not like if so. So the thing is like you for every component of the current you have an associated field that it couples to in the gravity sector, right? So stress tensor couples to the graviton, linearized graviton. Then you have the supersymmetric current that will couple to the gravitino and so on. But you don't have any current for, you don't have a separate current for the Lorentz transformation. So you don't get the spin connection as an independent field in the gravity sector.
So all these fields will be dependent.
Not all. You will yeah. The spatial conformal transformation and the local Lorentz transformation gauge fields will be dependent. That's why you need to impose these constraints. Will be dependent. As omega mu AB and F mu A will be dependent. So you will get only stress tensor and the dilatation current, right? That will couple to your metric, the graviton and the dilatation gauge field.
For
Dilatation,
I
yeah.
think
Yeah.
would still remain.
Yeah. Dilatation, yeah, dilatation, I mean, from the current multiplet, from the current analysis, you will not get the dilatation gauge field as such. So, because, yeah, we will see, like, later I'm going to discuss about current multiplets and all. We will see how these fields appear in the current multiplet analysis. Okay, but yeah, so the dilatation you will not get. Dilatation gauge field you will not arise out of the current multiplet analysis. You will not have any current which couples to the dilatation gauge field. So you will have a current, the energy moment, the stress tensor that couples to the graviton, and several other currents that couple to other fields to the multiplet. So here I'm talking about just pure gravity. There is no supersymmetry so far.
Yeah.
So we'll go in the supersymmetric analysis. We will see how current multiplets couple to different fields. That's the later part of my talk. So I will be discussing. Huh. Huh. Right. Yeah. So there will be no. B mu will not, in general, couple to any current. Yeah. Yeah. B mu won't couple to any current. So that has to be like put by hand, like.
Maybe
Yeah.
that you write on the next slide essentially delta dot.
No, the constant won't. So the constant won't determine B mu. Yeah, B mu is still an independent gauge field. So the dependent gauge field will be omega mu AB and F mu A. So B mu is still an independent gauge field, but somehow we'll see that it decouples from the action.
Okay.
The action won't be dependent on the B mu gauge field. Yeah. So yeah, so these are the constraints that one has to impose to convert this gauge theory into a theory of gravity. So the first one is essentially the torsionless constraint. If you expand the field strength corresponding to local translation, so you'll basically get this constraint as a torsionless constraint that will determine your spin connection in terms of the Weyl bind. So this is the usual constraint we know in terms of in gravity. The second one is the constraint which is telling you that the field strength associated to local Lorentz transformation is traceless if you contract it with the inverse Weyl bind, right? So this basically makes this Rm into a Weyl tensor. So if you expand this field strength corresponding to local Lorentz transformation and impose this constraint, which will basically tell you how F mu A is related to the other gauge fields, right? If you count the number of constraints, it matches exactly with the number of components that is there in F mu A and omega mu AB, right? So omega mu AB, the number of components, matches with the number of constraints that appears here, right? Because omega mu AB is antisymmetric in AB and mu is a free index. So here it is antisymmetric in mu and A is a free index, and the number will match 4 into 6. Right? It's antisymmetric in mu 6 into 4. That's exactly the number of components contained in omega mu AB. So the number of components in omega mu AB matches this constraint, and the number of components in F mu A matches this constraint. So that will, yeah.
Can you explain the origin of this constraint again for us?
Yeah. So these constraints. As I said, earlier I wrote out a gauge theory. So where local translation, local Lorentz transformation, these were local transformations, right? But in the theory of gravity, translation, you don't have local translation. What you rather have is a diffeomorphism, right? So if you want to convert, so the way to convert this local translation into diffeomorphism is by imposing certain constraints.
But why is this that constraint?
This is, I mean, any constraint would work, but these are what are known as conventional constraints. I mean, you can take some other linear combination of the field strengths, and
But
I mean
what I don't understand is that how is this constraint doing the job?
yeah, okay. So I have to go into a little bit details for that. I think it's yeah.
So that is
Yeah.
thought of the vanishing of the curvature.
Vanishing of the curvature for the local translation. Exactly. So that is essentially the torsionless constraint. So right, the torsionless T mu, I mean, the torsion is this is torsionless, which determines spin connection in terms of Weyl bind. Okay. So why this constraint? Yeah. So that one has to do a little bit of calculation to understand that. And unfortunately, I have not put that here, but it's very nicely explained in this book by Friedman and Brunfroen, supergravity book. The second one also essentially the same argument that so for example, so when you work out from gauge theory, how various gauge fields transforms under local translation, right? So you will see that if you find out how under local translation the Weyl bind is transforming, it will go to a general how E mu A should transform under general coordinate transformation plus some other terms that is proportional to this R mu A, right? So if you want the local translation to be realized as a diffeomorphism, as a general coordinate transformation, you would like that term vanishes, and that is why you impose this constraint. And the second constraint also arises in a similar fashion, and so these are the two constraints that are needed to realize the local translation as a general coordinate transformation. And the other symmetries that are there, other local symmetries will be present as local symmetries on the tangent bundle of space-time. Right. So that is how these constraints are imposed. And this will imply that omega mu AB and F mu A, which are the gauge fields corresponding to MAB and KA, will not be independent. They will be dependent gauge fields. Yeah. And so now if you count the number of degrees of freedom, so basically you have to count the number of components of all the independent gauge fields, and you have to subtract the number of symmetries. It will come out to be 5. Right. So if you want, you can. So the independent gauge fields are E mu A and B mu. These omega mu AB and F mu A are dependent gauge fields. So E mu A, if you count, just count the number of independent components, is 4 into 4, 16, and B mu is 4, so 16 plus 4, 20. And then the symmetries, you have 4 diffeomorphisms and 6 Lorentz transformation, 1 dilatation, and 4 special conformal transformation. So you subtract the number of symmetries from 16 plus 4, 20, 4 plus 6, 10 plus 1 plus 4, which is 15. So 20 minus 15 is 5. So you have 5 optional degrees of freedom. However, so the conformal gravity will have 5 degrees of freedom. Whereas Poincare gravity, the theory of gravity with only diffeomorphism has 6 degrees of freedom. The independent components of the metric is 6, right? So in order to go from conformal gravity to Poincare gravity, you need an additional degree of freedom, and that has to be provided by putting an additional field into your theory. These fields are called compensator fields. This compensator field compensates for the extra symmetries that is present in the conformal theory. Okay. So in this case, it will be like you need some field with 1 degree of freedom, and the natural choice is a scalar field. It has to have a non-vanishing Weyl weight because it has to compensate for the scale invariance, which is present in conformal gravity but not in Poincare gravity. Okay.
I'm sorry, where did conformality get in here in this?
Yeah, so this whole construction is a theory of conformal gravity, right? So whereas now I'm telling you how to go from conformal gravity to Poincare gravity. So you need to introduce additional scalar fields, additional fields. In this case, it is a scalar field because you count how many extra components you need. In conformal gravity, we counted that it is 5, whereas in Poincare gravity, it is 6. So you need an additional degree of freedom that is provided by this scalar field. And it needs to have a non-vanishing Weyl weight because it is going to compensate for the scale invariance.
For this 5, the counting of 5, I understood.
Yeah.
How does the 6 come?
6, the Poincare gravity has 6, right? Poincare gravity is described in terms of the metric, which has 6 components of shell. It's 10 minus 4. The metric has 10 components, and there is only diffeomorphism invariance.
But there is no this kind of. So that's 6 is
6 the theory of Poincare gravity. Just we are doing pure gravity. So pure gravity has 6 off-shell degrees of freedom.
So in both sides you are not taking into account Gauss law. In this side you are just counting the gauge transformation. Even on the gravity side you are just counting gauge transformation.
Gauge transformation.
Not any Einstein's constant. No Gauss law.
No. Yeah. So we are just counting the off-shell degrees of freedom, not the constraints that will be coming from. Yeah. So pure gravity, you have Weyl bind, which is 16. Just Weyl bind, which is 16, and you have 4 diffeomorphism and 6 Lorentz transformation. So that makes it 6. So pure gravity has 6 off-shell degrees of freedom, whereas conformal gravity has 5 off-shell degrees of freedom. So you need to introduce this extra scalar field.
That will be the trace of the stress tensor.
What?
Trace of the stress tensor. Which is 0 in the conformality theory. Not 0.
Right. Yeah. So, right. Yeah, I mean stress tensor and all these are coming from global symmetries. When you talk about supersymmetric field theory, not as such in gravity, right? But yeah, any field theory. I mean, just field theory it will be, I think. Right. Yeah.
They should match up, right? This is after all gauge theory for that.
Right. Yeah. So you introduce the scalar field, which has a non-vanishing Weyl weight. You take some Weyl weight for the scalar field, and you write down a conformally invariant action of the scalar field coupled to conformal gravity. So this is like you take the covariant derivative and just take double covariant derivative of that. This covariant derivative is covariantized with respect to the full conformal transformation, and by construction it becomes conformally invariant. So yeah, so phi has just one Weyl weight. You take you can take it to be anything, but let's take it to be 1. Let's take the Weyl weight of phi to be 1. So this is the covariant derivative of the scalar field, and then this covariant derivative will also once you convert it into this into the local Lorentz the flat index, that will also transform with respect to the special conformal transformation and as well as local Lorentz transformation. So the double covariant derivative will contain all these things. Okay. Where? This is the determinant, right? Determinant of E.
Oh.
Yeah.
I see. Okay. You are writing that.
Right.
Sorry.
Yeah. Yeah. Okay. I can write as E inverse L equal to this. Yeah. Right. Yeah, so you take the double covariant derivative, which is this, and then you know that omega mu AB and F mu A, these are dependent gauge fields. They are determined in terms of the other gauge fields. You just open it up. You write all the dependent gauge fields in terms of the independent gauge fields, and once you open it up, this Lagrangian simply becomes this. Okay, so this is still conformally invariant, and right, special conformal transformation. And omega mu AB is the spin connection. You replace them by the dependent, how they depend on the other gauge fields, and once you do that, you write it down, you get this. So this is still a conformally invariant action for the scalar field coupled to gravity. And now you use this scalar field to get, now as I said, so obviously F mu A and omega mu AB are dependent, so that goes away, but even the field B mu doesn't appear here. That doesn't, it's an independent gauge.
I have a question.
Yes.
So this 2 B mu is coming from where? B mu minus 2 B mu?
Yeah, 2 B mu, because this has now this, if you convert this into dA phi, so dA phi will have Weyl weight 2. Phi has Weyl weight 1. Okay. So dA phi, which is which you obtain by contracting it with the inverse Weyl will have Weyl weight 2, because the inverse Weyl has Weyl weight 1. So so that's how it happens. Phi has Weyl weight 1, dA phi will have Weyl weight 2. Yeah. So that is why this 2 B mu is coming. Yeah.
Yeah. Thank you.
Okay.
So have you done some partial integration here, because you had both derivatives acting on the phi.
Right. Yeah. I have done some partial integration. Yeah. To write it like this. Yes. Yeah. So that's what you get. And now you take this phi, and it has non-trivial scale transformation. So you use this phi to gauge fix the scale transformation by putting it to a constant value. Okay. So once you do that, the kinetic term of the scalar field goes away, and what you obtain is the usual, the Einstein-Hilbert Lagrangian for Poincare gravity. Right. So that is yeah. So if that is the way you come from conformal gravity to Poincare gravity. Okay. You can yeah.
Here you focused on the action associated with the new mode.
With the compensator field.
But there is
The rest of the stuff also. That's so that will typically give you higher derivative terms. So that's what I was going to talk. So you can also write down a conformally invariant action made out of the purely out of the gravity sector, which is basically this. So this is not Riemann tensor. This is the field strength associated with the local Lorentz transformation. So this is Rm mu nu AB. Okay, and upon imposing the constraint, this basically becomes Weyl tensor. So this is essentially the Weyl tensor square, which is also conformally invariant. And yeah, so this is nothing but the Weyl square term. And you can also couple it to the scalar field that you have introduced. But in order to make it conformally invariant, you need at least 2 scalar fields. You cannot couple it to just one scalar field, because you cannot construct anything out of one scalar field which is scale invariant. Right? So you need at least 2 scalar field with the same Weyl weight, so that you can take the ratio and take an arbitrary function of that ratio, which will be scale invariant, and you can couple that to the so that will essentially give you the higher derivative terms for Poincare gravity. After now you can use one of the scalar field to gauge fix the scale transformation, and then essentially only one scalar field will remain in your theory. So you'll have gravity coupled to one scalar field. So you'll get the Einstein-Hilbert action and the higher derivative terms coupled to that scalar field. Okay. Yeah. 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 Field strength of the local Lorentz transformation.
So the local Lorentz transformations, the gauge field already had mu and an E. So now when you take a derivative, you're taking a derivative with the local.
Yeah. So omega mu. This is the field strength corresponding to omega mu AB.
Yeah.
Right. So omega mu AB is the gauge field. So the field strength is R mu AB. Yes.
Okay.
Yeah. Right. So once so that will also have the special conformal transformation gauge fields in there, and once you impose the constraint and replace the F mu A in terms of the independent gauge fields, you can see that this is actually a Weyl tensor.
Exactly the Riemann tensor or
No, no, it will be Weyl tensor because Riemann tensor will not have this constraint. This constraint, this will not be satisfied by Riemann tensor. This is satisfied by Weyl tensor. Yeah, so so this will be Weyl tensor.
But this construction d omega plus omega with omega, isn't that exactly what I
But there is,
done for?
but there is a f mu a also, because this r mu nu ab will have terms contributing from f mu a, the special conformal transformation gauge fields, because omega mu ab transforms under. Yeah, omega mu, this there is a non-trivial structure constants coming from NAD.
It's a full non-linear.
Yeah, yeah. Right. Yeah.
The term starting from the gauge field associated to the special conformal transformation. Starting from the special conformal transformation gauge field. And can you construct a gauge invariant action?
Starting from the special with RK. Okay, so RK. So once you impose these constraints, you will see that there are the Bianchi identities will imply several more constraints, and one of the constraints will be that RK will not be independent anymore. It will be related to some covariant derivative of Rm that can be shown. So RK is not an independent curvature.
If you were to write something, it would essentially be higher derivative.
Yeah, higher derivative Rm. Yes. Sure. So that's basically about conformal gravity. So you know, in generalization, so in the next slides we'll see how to generalize this to conformal supergravity.
Gravity is just this Weyl square term.
Yeah, the pure conformal gravity is just the Weyl square term. Yeah, and supersymmetrization, supersymmetric conformal gravity will be the supersymmetrization of this Weyl square term. And the important thing here was that because essentially we are interested in Poincare gravity, not in conformal gravity. So conformal gravity is an intermediate step to reach Poincare gravity. Of course, you know, you can write down Poincare gravity. You can write down Einstein-Hilbert action just from the symmetries of Poincare gravity also. But in supersymmetric gravity, if you want to construct some off-shell Poincare gravity theories, this is one of the ways to do it. I don't know if there is any other way to construct it, but this is certainly one of the way to do it. To first, right. Conformal off-shell. If you want off-shell formulation, this is the only way I know so far how to do it. Yes, yes. Right. I mean, yeah. So I mean, it's. I think it's essentially conformal gravity gives you a good handle on how to work with these degrees of freedom, and yeah, I don't know, like the. So if yeah, I don't know the answer to this, but this, yeah. So why he.
One can think of writing down optional formulations
Huh.
of this usual supergravity as one of the units. And approaching that question from
Conformal
supergravity is
that
gives you
a good handle on the construction.
why because the thinking is the same. You just have gauge fields and then impose symmetry and write down action. Why can't you do it better for conformal supergravity as opposed to just supergravity?
Yeah, so you're asking like why can't we start with just the Poincare, super Poincare algebra, and essentially do the same thing that we did for superconformal? I don't know. I think maybe finding the representations of the Poincare algebra would be a harder thing to do. Maybe, I don't know. But writing down conformal algebra and then introducing compensating multiplets, yeah. Turns out to be, I don't know, but this is one of the ways in which it is, and this is the only way so far I know in which it is done. Okay, so what, like, yeah, so conformal supergravity is, yeah.
This S plus phi with phi 1 by
Phi 2, yes.
And here also
phi 1. One of the scalar fields can be used as a compensator, the other scalar field will remain. Right. Right. Suppose you just add one compensating scalar field, then essentially you will end up with just gravity with high derivative terms. But if you
Put this f of s completely to 0 by some gauge fixing?
not really, because f of s, see, this is the scale invariant function, so it doesn't like you cannot use f of s to gauge fix because that's scale invariant. So you can use one of the scalar field to gauge fix. So either phi 1 or phi 2. Then what will happen is that in the gauge fixed version,
Phi 1 is equal to 0.
or 0.
Then this is f of s.
Oh, 0 will be non-trivial. 0 like because
f of 0 would still be non-zero, right?
yeah, but setting the scalar field to 0 is like yeah. So you want to gauge fix the scale invariance, right? So phi goes to w phi, delta phi is w phi. So setting phi to 0 doesn't fix the gauge invariance. You have to fix it to a constant, some constant value. Yeah.
I see.
Yeah.
So that's a bad.
Yeah.
Perhaps one disadvantage
Uh-huh.
goes to the question of supergravity from conformal supergravity.
Uh-huh.
You cannot, probably won't be able to do integration behind it because
There is no official formulation. Yeah, right. So far it is done till 6 dimensions. Yeah, and also not for like for there is certain limit on the number of supersymmetries which you can do. Like in 4 dimensions, you can do up to n equal to 4. Also, like conformal supergravity will have official formulation, but in n equal to 4, since you need the one compensating multiplet to go from conformal to Poincare, the compensating multiplet in n equal to 4, for example, is vector multiplet, which is on shell. So in the end, you will not be able to formulate an off-shell theory of Poincare supergravity. You will only be able to construct an on-shell theory of Poincare supergravity for n equal to 4. Full off-shell will work only for n equal to 2 in 4 dimensions. Similarly, in 5 and 6 dimensions, it will work only for the minimal supergravity. And yeah.
saying that in 7 or higher dimensions,
Yes.
you don't have
No. No.
superconformal
No.
algebra.
Yeah. Right. Yeah, so essentially what you do is just like what we discussed in conformal gravity. You start with a gauge theory of the full superconformal algebra and introduce gauge fields corresponding to each generator, and then you convert the local translation into general coordinate transformation by imposing constraints. So the two of the constraints are essentially almost the same as what I discussed earlier, but supersymmetry will also demand more constraints. For example, you will get one more constraint which will determine, so in the superconformal algebra, you have 2 kinds of supersymmetry. There's something called the Q supersymmetry and something called the S supersymmetry. Right? So you will have gauge fields associated with this supersymmetry. So one of the constraints will make the gauge field associated with S supersymmetry to be dependent one. And the gauge field corresponding to Q supersymmetry will become the gravitino. Yeah, so that will be there, and then however, this the story doesn't end here for superconformal gravity, because you will see that just by having the independent gauge fields, the number of bosonic degrees of freedom and fermionic degrees of freedom will not match in general for extended supersymmetry. It does match for the minimal supersymmetry, but it will not match for the extended supersymmetry. So just the gauge fields won't be sufficient, and you have to complete the field representation by adding some additional auxiliary fields into the multiplet. Okay? So you have to complete the field representation by adding additional matter fields, and then you have to also modify the transformation rules that you got from the superconformal algebra. And then your algebra will also be modified by what are known as soft terms. There will be field dependent terms in the algebra. If you take QQ commutator, the usual superconformal algebra will tell you that it goes to a translation, but here if you take QQ commutator, you will go to a general coordinate transformation plus several field dependent gauge transformations. So that is how the algebra will also be modified. So that is the difference when you go from gravity to superconformal gravity. Okay, so in this way you obtain what are known as the Weyl multiplets of conformal supergravity. So they contain, as I said, the gauge fields of the superconformal algebra, the independent gauge fields of the superconformal algebra, plus additional matter fields that you need to put in to complete the field representations. So yeah, so this is the Weyl bind, which is the gauge field corresponding to local translation. This is the gravitino. This is the gauge field corresponding to Q supersymmetry. This is the dilatation gauge field, and you have SU2 and E1 are symmetry in n equal to 2. So these are the gauge fields corresponding to SU. This is SU2 gauge field, and this is the E1 gauge field. And then you need to add these extra matter fields to complete the field representation. So this is an antisymmetric in AB and antisymmetric in IJ. So when I write it like this, it's actually anti-self-dual. Okay, since it is n equal to 2, I can essentially take this IJ out by writing this TAB IJ as epsilon IJ times some antisymmetric field, right? Then you have this chi I, which is a Majorana spinner, and then you have a real scalar D of Weyl weight plus 2. So this is your n equal to 2 Weyl multiplet, and this was worked out by Berkshu, Deroux, and DeWitt long back in 1981. Yeah. 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 No one. Yeah, but yes. So once you solve the constraints and you count the number of components of these gauge fields, you see that the bosonic and fermionic degrees of freedom are not matching, right? So.
Because you started with a bunch of gauge fields which had same number, then the symmetries were the same number.
I will do the counting in the next slide. You will see. So then you have n equal to 4 Weyl multiplet also. That was also worked out in this paper. So n equal to 4, you have the gauge fields. So you can see that there is no E1 R symmetry gauge field here because n equal to 4 doesn't have E1 R symmetry. And then you need this bunch of matter fields to complete the field representation. Okay, so this, for example, this has the same symmetry properties as this in n equal to 2. This chi ijk will belong to the 20 of SU4. This is antisymmetric in I and J and traceless in Ik and Jk. So this is 20, and this is antisymmetric in IJKL and traceless in any up and down index. This is belongs to the 20 prime of SU4. And then you have EIJ, which is basically symmetric in IJ, so that's the 6 of SU4. And then you have lambda I, which is a doublet of Majorana spinners. And this phi alpha, this index alpha is carries 1 and 2, and these are constrained in the sense that phi alpha is equal to 1, where this phi upper alpha is related to the complex conjugate of phi alpha. Eta is 1 minus 1, diagonal 1 minus 1. Space time? Yeah, psi mu I. That's the yeah, I'm not writing down phi, for example, phi mu I. That will be that will correspond to the S supersymmetry. That's a dependent one. I'm not writing that down. Yeah, I'm just writing down the independent one. Yeah. 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 So this is like this is the doublet of complex scalars, and upon imposing this constraint, this becomes actually 3 complex scalars. 3 complex scalars. So there is the physical. However, this has a spurious E1. This will have a spurious E1. That's not the R symmetry, but this will have in this construction it will have a spurious E1. So the physical scalar will still be a complex scalar in n equal to 4. So there are 3 scalars here, 3 real scalars, and there is a spurious U1 which will can be fixed by one of the components of this thing. No. This is not the alpha dot index. This is a SC1,1 index. So this thing has a SC1,1 symmetry, and this has a SC1,1 invariance, and there is a spurious E1, and the physical scalar will be in the SC1,1/E1 coset. So these are basically coset scale. The physical scalar will be a coset scalar. It's in the construction itself. It comes yeah. Yeah, so that is in the conformal algebra. But when you construct this Weyl multiplet, you will see that you will need, there will be a C1,1 symmetry that also comes in. That's a global symmetry. That's not a gauge symmetry. That's a global symmetry. But there will be a spurious local E1 also in this construction, Because essentially what you're doing when the physical scalar is a complex scalar. So what you're doing is essentially you are putting in a local, you are putting in a spurious E1 and adding one extra scalar field so that you are able to write down the supersymmetry transmission in a better way. That's the only thing. Like to be able to write down. But while doing this, huh? Hmm? Yeah, so like so when you have a complex scalar, right? So there is a SL2R that you can always have, right? That's essentially the SU1, 1. Yeah, there is no complex scalar here, right? There is no complex scalar here. So here you don't, the additional matter fields are this, and you have only a real scalar which is Weyl with 2, and right. So here in this n equal to 4. Why? Yeah, you can associate a U1 gauge symmetry and if you have a complex scalar, you can also have a global SL2R symmetry, right? That takes it to A tau plus B by C tau plus D, right? So that's so that's what it is. Like like what kind of matter fields you need to add to complete the Weyl multiplet, that has a procedure to it, right? You start from some current multiplet of like associated with the global vector multiplet, and then to each component of the current multiplet there will be a field, and that's how you obtain the linearized Weyl multiplet. And then the linearized Weyl multiplet you can just systematically complete its supersymmetric transformation. So there itself, from the current multiplet itself, you will see that you have a complex scalar current which will couple to a complex scalar field in the Weyl multiplet, right? So you have a complex scalar field in the Weyl multiplet. So in the linearized Weyl multiplet you have a complex scalar field, right? Then when you complete the field, the linearized Weyl multiplet into the full nonlinear Weyl multiplet, then these people saw that it's a nice way of rearranging the degrees of freedom, and where this alpha index is the SU1, 1 index, and there is a spurious E1 that comes in which takes care of the extra degrees of freedom that you have. So you have basically 3 scalar fields here, but there's an extra U1 that you have introduced which makes the physical scalar to be 2 degrees of freedom. Yes, this is the 4-component spinner. So depending on whether you want to write it in a 2-component form or 4-component form, you can have the alpha dot index. So this will be. In addition to mu, there is an additional. Yeah, no, this mu is the space-time index. This mu is the space-time index. I is the SU2 index or SU4 index depending on where you are. But this is the 4-component spinner, and having it's a 4-component. It's a left chiral 4-component spinner. So the way it is written, if you have upper I, it's a left chiral. Then the lower I will be related to the Majorana conjugate of this upper I, that will be right chiral. Okay, so this will have an alpha index, and the lower I will have an alpha dot index. Yeah, so that's the spinner index which I am not writing here. Yeah. Right. Okay, so let us do the counting. So n equal to 2, if you see, I just wrote down the independent fields here. So the independent gauge fields. So these are bosonic ones. I just wrote down the independent gauge fields corresponding to the bosonic fields and the matter fields that we had added. So if you just count the number of components without worrying about the symmetries and all, just count it like this is 4 into 4, 16, this is 4, this is 4, this is 4 times 3 because this is SU2, that is 12, and this is antisymmetric, so this is 6, and this is antisymmetric in SU2, that is 1, so that is 6, and D is essentially 1. And then you look at the bosonic symmetries where diffeo, local Lorentz transformation, special conformal transformation, dilatations, E1 and SU2. So you take the number of symmetries, the bosonic symmetries, okay, and you just add this up, and you just add this up, and then subtract these 2. Okay, then you'll get 24. And similarly for the fermionic symmetry, so this is a gravity, so this is this is 4 into 2 because it is SU2. 4 into 2 is 8, and this is a 4-component spinner. It's a Majorana spinner, so 8 into 4 is 32, and this is essentially 2 into 4, that is 8, and these are the number of symmetries Q sub C and S sub C. So 40 minus 16 is 24. So the number of components, bosonic components and fermionic components matches. Now you can see that if you didn't have this chi I, for example, so what will be the number of fermionic components? It will be 32 minus 16, which is 16. And the number of bosonic components, for example, it will be 16 plus 4 plus 4, 20. And this is 4 plus 6, 10, 14, 15, 16. Sorry, this is 10, 14, 15, 16, 3, 19. Okay, so this is 32. Sorry, this is also included. So 32 minus 19, 16 plus 4, 20, 24, 36. 36 minus 19 is 17. So 17 bosonic degrees of freedom and 16 fermionic degrees of freedom if you didn't have this extra fields in the multiplet. So these extra fields are needed actually to match the number of components. Okay. If you do the same for n equal to 1, for example, you will see that the gauge fields alone are sufficient. The gauge fields will match the number of, so there is no additional matter fields that is needed for n equal to 1, for example. But n equal to 2 and 4, it will be required. Okay. So, yeah. So n equal to 4 also you can similarly count, and you will see that the degrees of freedom matches, and it's 128 plus 128 for n equal to 4. Okay. Okay. So that's roughly what are the Weyl multiplets of n equal to 2 and n equal to 4. So let me briefly discuss about the Weyl multiplets in 5 and 6 dimensions. I will not give the details of that, but what I will essentially say is that in 5 and 6 dimensions, it has been seen that there exist 2 different versions of Weyl multiplets for minimal supergravity. So what are these 2 different versions of Weyl multiplets? So these multiplets differ in the content of their auxiliary fields. So as I said, you need to add these extra fields to complete your field representation. But what fields you add, okay, that can be different. Okay. So in 5 dimensions, it has been seen that there are 2 different versions of these Weyl multiplets. So the first one is an old paper in 1986 by Bockschub, Seskin, and Van Froen. That yeah. Yeah. Hmm.
Is there a unique coupling to the conformal supergravity that's important?
If you give me a n equal to 2 superconformal field theory.
So I give you the stress tensor.
Yes, yes, yeah. So depending on what superconformal field theory you are giving me, the coupling can be different. Like for example, if you give me a superconformal field theory corresponding to a vector multiplet in 4 dimensions, right? The vector multiplet, stress tensor that I get from there will be traceless, right? Because the free action for a vector multiplet is scale invariant.
Any stress tensor for conformal field will be traceless.
Yeah, not right. So okay, superconformal field theory, right?
Yeah,
so superconformal, right. Yes. Yes. Right.
And then
Yes.
the coupling would be
Uniquely fixed. Yeah. So if I know the full current multiplet of this, right. So if it's a superconformal field theory, yes, you're right. That it will be traceless. So, but whether it uniquely couples to this Weyl multiplet or to the superconformal gravity or not, that I am not sure. For example, if you take tensor multiplet, if you take the free action of a tensor multiplet, that is not scale invariant. But of course, it is not a superconformal field theory. So, but there is something called the improved tensor multiplet. You can write down scale invariant action. Improvements are done, and then you get if you give them whether the current minimal right. Exactly. Right. Yeah, so that's essential. Like if you give me the current multiplet of a superconformal field theory, that will essentially couple to the Weyl multiplet, right? That's true. I think it should be the same. If they come from a superconformal field theory, it should be the same. But I have not done this. I also what I have done is what I'm going to discuss is that the real question of interest comes when you are coupling a non-conformally invariant field theory to gravity, where this is the place where they get the dilaton Weyl multiplet. Okay, so
that's
here.
We have to modify the field content of this also.
Yes.
by adding this, how compensated?
Yes, yes, yes.
Yeah.
So okay, so basic, okay, so the way this Weyl multiplets in n equal to 2 and n equal to 4 in 4 dimensions were discovered is by actually going by taking this vector multiplet action that's conformally invariant. So you work out the current multiplet corresponding to the vector multiplet, and corresponding to each component of the current multiplet, it will couple to a field of the Weyl multiplet. And once you know the supersymmetric transformation of the current multiplet, you can work out the linearized supersymmetric transformation of the field that they coupled to. And that's essentially how you get the linearized Weyl multiplet. And then it's a matter of just completing the nonlinear terms and modifying the algebra and all these things. But that's essentially how you get the Weyl multiplets. Okay, but whereas in 5 dimensions, okay, yeah. So okay, let me. I'm coming to that. So yeah, so what I was saying is that in 5 and 6 dimensions, it was seen that there exist 2 different versions of these Weyl multiplets. Okay, one of the version contains a real scalar field of a non-vanishing Weyl weight, and this multiplet is referred to as the dilaton Weyl multiplet. You can always interpret that scalar field as a dilaton. And the other version is known as the standard Weyl multiplet, which is basically related to the n equal to 2 standard Weyl, the Weyl multiplet that I had discussed earlier. This is called standard Weyl multiplet, which has this auxiliary fields Tab, Ij, Chi, and D. Okay, so there is a version in higher dimensions also, which is related to that standard Weyl multiplet by a dimensional reduction or uplift.
These
Okay.
two possibilities are there even for non-supersymmetric conformal gravity?
If it's a non-supersymmetric conformal gravity, you don't add these extra fields. These extra fields we needed to add because of supersymmetric theories. Yeah. So the dilaton Weyl multiplet has extra gauge symmetries other than the superconformal symmetries, and there is a relation between the gauge invariant quantities of this dilaton Weyl multiplet and the auxiliary fields of the standard Weyl multiplet. Okay. So how? So in 5 dimensions, this dilaton Weyl multiplet was constructed via 2 procedures. Okay, so one of the procedure is what was done is that a vector multiplet was taken and it was coupled to a standard Weyl multiplet. Okay, and the vector multiplet equations of motion were used to replace the auxiliary fields of the standard Weyl multiplet in terms of new auxiliary fields of the dilaton Weyl multiplet. Right, that's how you basically got the dilaton Weyl multiplet, and also the relation between the standard Weyl multiplet auxiliary fields and the gauge invariant quantities of the dilaton Weyl multiplet. Okay. The other way which is interesting is that just like they did in 4 dimensions, if you approach the same way, that you take a vector multiplet, a field theory corresponding to the vector multiplet in 5 dimensions, and look at its current multiplet and see how it couples to the fields of a Weyl multiplet. But if you write on a free action for a vector multiplet in 5 dimensions, it is not conformally invariant. So F mu is not scale invariant in 5 dimensions, right? Right? Yeah. So if you write on a free action corresponding to the vector multiplet, that will not be scale invariant. So the energy momentum tensor that you get from there will not be traceless. Okay. So the trace of the energy momentum tensor will be a non-trivial component of the current multiplet that you get. Okay, and so this trace of the energy momentum tensor will couple to a scalar field in the Weyl multiplet. So in this way, the Weyl multiplet that you will get will have a scalar field with non-vanishing Weyl weight, and that will be the dilaton Weyl multiplet, right? And in 5 dimensions, essentially they work both and in both the approach, and they got the same dilaton Weyl multiplet. Okay. In fact, the standard Weyl multiplet was also discovered by using this. Like, you start with you get a dilaton Weyl multiplet, and then you realize that there is some combination of these dilaton Weyl multiplet fields, which if you define that to be your Tab, Ij, and Chi, and D, then the transformation looks more like the standard Weyl multiplet transformation. So that is how the standard Weyl multiplet and dilaton Weyl multiplets were discovered in 5 dimensions. Okay. So, so what we will see is that we will, yes.
This is the question that I asked before. If I were to couple these two different types of multiplets to SCF2, would I get the same theory of gravity coupled to matter, or different? I mean, are these things physically different, or just
relatively? Okay, so these things are see they carry the same number of degrees of freedom, and there is a relation between the standard Weyl multiplet fields and the gauge invariant quantities of the dilaton Weyl multiplet. But these relations, I won't say they are not invertible, but so far nobody has been able to invert them. So whether this is a one-to-one relation, your question is whether these are equivalent multiplets.
Right.
I would say if they are equivalent multiplets if there is a one-to-one relation between the fields of the standard Weyl multiplet and the fields of the dilaton Weyl multiplet. First thing is that the dilaton Weyl multiplet has extra gauge symmetries, which is not there in standard Weyl multiplet, right? However, the gauge invariant quantities of that, like gauge invariant quantities corresponding to those gauge symmetries, are related to the standard Weyl multiplet auxiliary field. So you can find a relation between TAB and the gauge invariant quantities of the dilaton Weyl multiplet. Similarly, chi I and the gauge invariant quantities of the dilaton Weyl multiplet, D and the dilaton Weyl multiplet. Okay.
That gauge symmetry is this vector multiplet.
Yes, so there will be a gauge symmetry coming from this vector multiplet, and we will see that there is some more gauge symmetry that will arise when you try to solve these equations from motion. We'll see. We'll see that I will not discuss 5 dimension. I will discuss more or less our work on 4 dimensions. We'll see how this comes. Okay, so we'll use this first method where we couple this vector multiplet to the standard Weyl multiplet and use the equations of motion to replace the standard Weyl multiplet auxiliary fields in terms of the dilaton Weyl multiplet auxiliary fields, and that's how we will construct the dilaton Weyl multiplet in 4 dimensions. However, we'll see that if we use the second method, where we start from a non-conformal matter multiplet and use its free action to write down the current multiplet and see what components it couples to, we will see that instead of discovering the dilaton Weyl multiplet, we will discover a new matter multiplet, and this scalar field that couples to the trace of the energy momentum tensor actually sits inside that new matter multiplet, and which we call as a real scalar multiplet. So that is what we will see. Unlike 5 dimensions where both the approaches gave the same dilaton Weyl multiplet, here we will actually discover 2 new multiplets. Okay. So let us. So let me first. I will discuss about this dilaton Weyl multiplet. So I will give you the results first, and then I will talk about the construction. So these are the. This is the result of the dilaton Weyl multiplet. So you can see that in the gauge fields now I don't have a U1 R symmetry gauge field. Okay. What happens is that this U1 R symmetry gauge, U1 R symmetry is there, but the U1 R symmetry gauge field is no longer independent. So in this dilaton Weyl multiplet, the E1 R symmetry gauge field is actually dependent, and then you have this extra matter fields that you needed that will replace your TAB, IJ, chi I, and D for the standard Weyl multiplet. So you have a complex scalar that this comes from the vector multiplet, and you have a gauge field. This also comes from the vector multiplet. But now you have one more gauge field, which I write as W tilde mu. This will come when we try to solve the equations of motion. And you also have a tensor gauge field. Okay, you have 3 extra gauge symmetries here. One corresponding to this one U1 gauge transformation corresponding to this gauge field. One more U1 transformation corresponding to this gauge field, and a vector gauge transformation corresponding to this tensor gauge field. Okay, so these are the additional gauge symmetries that will be there in the dilaton Weyl multiplet. And so if you now count the number of symmetries and count the number of components, you will see that there is once again bosonic component is 24. Similarly, your fermionic components is the same counting essentially, because your chi A has been replaced by omega I. So only the the Weyl weight will change of this omega y vis-a-vis what chi I had, but essentially the counting will be the same. So once again it has 24 plus 24 degrees of freedom with some additional symmetries here. Okay, and this is the full gauge transformations. Okay, so just took a screenshot from our paper. It's not important, but yeah. And the E1 R symmetry gauge field is essentially a dependent gauge field that is coming from this. You can think of this as a constraint that determines your E1 R symmetry gauge field in terms of the other fields of your theory. So that's the difference between dilaton Weyl multiplet and the standard Weyl multiplet, where E1 R symmetry gauge field also becomes the independent gauge field. Okay, so let me briefly tell you about the construction. So as I said, for the construction, you start with the vector multiplet and couple it to the it to the standard Weyl multiplet. So the vector multiplet n equal to 2 vector multiplet contains a complex scalar which has Weyl weight +1 and chiral weight -1. Chiral weight is basically how it transforms under the E1R symmetry. And then you have an SU2 doublet of Majorana spinor, which left chiral component omega I has Weyl weight 3/2 and chiral weight -12. You have an abelian vector field with both Weyl and chiral weight 0. And you also have an SU2 triplet of pseudo real scalar field Yij with Weyl weight 2 and chiral weight 0. Okay, and this is the way they transform, okay, under Q supersymmetry as well as S supersymmetry, where this gamma that appears in the transformation of Yij is essentially this combination of d slash omega and x ij, and this f hat that I have written here is a linear combination of this. This is the supersymmetric invariant, this is a supersymmetric covariant field strength associated with omega with W mu, and these are some terms proportional to T mu ij. Okay, so this is the definition of f hat that appears in this supersymmetric transformation. Okay, so now we need to write down the equations of motion of this vector multiplet. So you can write down an action of the vector multiplet coupled to the standard Weyl multiplet and derive the equations of motion. But the easiest way to do would be to start with some lowest equation of motion and then using supersymmetry get the other components of the equation of motion. So the lowest component of the equation of motion will be Yij is equal to 0. It's the equation of motion corresponding to Yij, and Yij has Weyl weight 2. So the equation of motion corresponding to Yij should also be Weyl weight 2. Okay, and that's nothing but Yij itself. So Yij is equal to 0 is one of the equation of motion, and the other equation of motion you simply apply supersymmetry transformation on that, and you okay. So if you apply supersymmetry transformation on Yij, you get this. So the other equation of motion will definitely be gamma I equal to 0. That's what this is. And then you take this gamma and apply supersymmetry transformation on this. You will get the other equations of motion. Okay, so these are essentially your equations of motion. Okay, so let us look at the fourth equation of motion. So okay, this should be calligraphic f, which this f hat is the same f hat that I have here. Okay, so if you let us take this equation of motion. So in general, this is a complex equation of motion. Okay, but if you take its, you can take its real and imaginary part. Okay, if you take its imaginary part, okay, that will be automatically satisfied because of the Bianchi identity of this. So I have not written down, but there will be Bianchi identity corresponding to this f. And once you take into account that Bianchi identity, the imaginary part of this equation will be automatically satisfied. So what you have to really solve is the real part of this equation. And the real part, you can essentially write it like this. Okay. So now look at this. So what you can see is that if you take these things inside the parenthesis and define this to be the dual of some field strength in this particular way, so this equation essentially becomes the Bianchi identity for this field strength, right? This simply becomes this. Okay. Okay. So what you can so basically what I'm doing is I'm solving this equation in terms of a field strength of a new gauge field. Okay. So that that equation of motion becomes a Bianchi identity for that gauge field. Okay. And using this equation, your auxiliary field T and T plus and T minus. So T plus AB is basically TAB IJ. So T plus AB is basically epsilon ij, TAB ij, and T minus AB is epsilon ij, TAB ij. So since this is SU2, I can contract it with an epsilon ij and write those as my T plus and T minus. Okay, SU4 it won't be like this. I mean, since it is SU2, it's a singlet. Anything antisymmetric in ij is a singlet. Right, so I can do that, and so basically I can use this equation to solve for T plus AB in terms of the field strength which was associated with the vector gauge field already present in the vector multiplet, and the field strength of the newly introduced gauge field, which I call as W tilde mu. Okay. So right, and then from this relation, you know already how FAB transforms you know already how x and t plus and x bar and t minus transform. From this, you can find out how the field, newly introduced field strength will transform. And then you basically use that and the Bianchi identity and the supersymmetry algebra. It will be a lot of some work has to be done, but essentially using those three things, you can find out how the gauge field corresponding to this field strength will transform. Okay. And suppose you don't do that, but I give you this transformation, you can go back and check that all the things are satisfied. Like if you from this you can find out how the field strength should transform, and that will essentially match with what you get from here. You can find out what is the Bianchi identity, and that should match with this. And you can act the algebra, the commutator of a delta q on this, and that will satisfy the algebra also. Okay.
These two
Yeah.
descriptions are same on the equation of motion, right?
Yes. Yes.
Once you have equation.
Yeah. So essentially, what I'm doing is I'm adding an extra vector multiplet to the standard Weyl multiplet. So the number of components becomes 24 plus 24 plus 8 plus 8, which is 32 plus 32. And now what I'm doing is I'm using the 8 plus 8 equations of motion of the vector multiplet to remove this to remove the auxiliary fields of the standard Weyl multiplet in terms of the new auxiliary fields.
How come the supersymmetry algebra guaranteed to both auxiliary?
Yes, yes, yes. That's what. Because now what I'm doing is this equation of motion is becoming a Bianchi identity. So it's not an equation of motion anymore. It's a Bianchi identity, right? Yeah. Then this is how the fourth equation you use to solve for TAB in terms of this field strength. Then the third equation, which was gamma j equal to 0. Gamma j is essentially the linear combination of d slash and x chi that you can use to solve for chi in terms of the vector multiplet fields. That's simple enough. Whereas this c is equal to 0. That's a complex scalar equation that has two components. Okay, you can take the real and imaginary part. If you take the real part, you can solve for the auxiliary scalar d of standard Weyl multiplet in terms of the vector multiplet fields and the newly introduced field strength. This is the relation between d and the fields of the dilaton Weyl multiplet. And the other component, the imaginary component of C, will basically give you a constraint on the complex scalar x of the vector multiplet. So this is that constraint. Okay. So now once again, this constraint also, if you look at the things inside the parenthesis, this constraint can once again be solved if you think of these terms inside the parenthesis as a dual of a three-form field strength, because this carries one index. Okay, so you can think of these terms inside this parenthesis as a dual of a three-form field strength. Okay, so if you write these terms inside the parenthesis as a dual of a three-form field strength, this constraint essentially becomes a Bianchi identity on this three-form field strength. Okay, okay, right, and this equation becomes a constraint on the E1 R symmetry gauge field. This is exactly the same constraint that I showed you when I was discussing the result. So now if you can see that why it determines how it determines your E1 R symmetry gauge field. If you open up this covariant derivative, you can see that this is the equation that you get, and this essentially tells you what is the E1 R symmetry gauge field in terms of the other fields of your dilaton Weyl multiplet. Okay. And again, like using the same approach, like finding how this three-form field strength transforms, because you already know how x bar omega k transforms. From there you can find out how h abc transforms, and then from this Bianchi identity and the supersymmetry algebra, you can find out how the gauge field, the two-form gauge field corresponding to this three-form field strength transforms. And this is exactly what you get. This is exactly what you get. Okay.
Can I please visualize the sophisticated version of the visual duality where the equation of motion for one becomes the
Bianchi identity. Yeah, but here it's like, yeah, so equation of motion. So for example, here the equation of motion of the vector multiplet is becoming the Bianchi identity of the new gauge field that I'm introducing. But that I am making sure by yeah, so that is true. So yeah, but now once after these are part of the dilaton Weyl multiplet. Yeah, so the thing is that yeah, so if your TABIJ of the standard Weyl multiplet is of that form, yes, yeah. So for example, if TAB of your standard Weyl multiplet is of this form, then the equation of motion for the dilaton Weyl multiplet becomes the Bianchi identity of this. So yeah, right. So what here you are, yeah. So this is the equation of motion of the vector multiplet coupled to standard Weyl multiplet. Okay, but after you do this, then what you get is the dilaton Weyl multiplet. There is no standard Weyl multiplet anymore, right? So there the equation of motion of the gauge field will be different, right? Yeah. Yeah. So here, yeah. So right. So this is how you obtain the supersymmetry transformation of the two-form gauge field, right? Right. So so essentially now what you have done is you have replaced your auxiliary the matter fields that you had in standard Weyl multiplet TAB, IJ, chi I and D, as well as in the last step what we saw is that the U1 R symmetric gauge field also becomes dependent. Okay, and the new auxiliary fields of your multiplet are basically the complex scalar field of your vector multiplet, the gauge field of your vector multiplet, and you have introduced a new gauge field and a new tensor gauge field in order to solve these equations of motion. So those become your auxiliary fields, and E1 R symmetric gauge field is removed from the content of the gauge field because it becomes a dependent gauge field, and you essentially get the dilaton Weyl multiplet that I had discussed in my results section. Yeah. Okay, so you have E mu A, psi mu I, B mu ij, and x omega I comes and W mu comes from the vector multiplet, and this omega tilde W tilde mu and B mu nu comes while solving the equation of motion. And you have extra gauge symmetries corresponding to this W tilde and B mu nu. Yeah, so that is essentially how you construct the dilaton Weyl multiplet in n equal to 2. Yeah, so now next step, so while so I will discuss about this new multiplet. I don't know how much time we have. How much time is left?
Well, we can go up to 1 o'clock for sure. How much time?
I think I can finish in another 10 minutes.
Yeah.
Okay, so recall what I said about 5 dimensions. There were 2 approaches to construct this dilaton Weyl multiplet. One of the approach is exactly what I discussed earlier for 4 dimensions also. Yeah. So the other approach where the current multiplet corresponding to a non-conformal matter multiplet was found out in 5 dimensions. So if you do the same thing, however, one has to realize. Yeah, so you have to find the current multiplet and then find a linearized supersymmetry transformation of the Weyl multiplet, and then finally complete the supersymmetry transformation systematically. Okay. However, in 4 dimensions, vector multiplet is conformal, meaning if you write on the free action for the vector multiplet, it will be conformally invariant, and that is how the n equal to 2 standard Weyl multiplet was discovered by looking at the current multiplet corresponding to the vector multiplet. Okay, so in order to get something close to dilaton Weyl multiplet, we thought we have to start with some matter multiplet whose free action is non-conformal. Okay, and the natural choice was the tensor multiplet, because if you take tensor gauge field field strength square h mu nu rho, that will not be scale invariant in 4 dimensions. Okay, and therefore the energy momentum tensor will not be traceless, and the trace of the energy momentum tensor will be a non-trivial component of the current multiplet, which will couple to a real scalar field, and you might expect to get something like the dilaton Weyl multiplet. Okay, so you start with a tensor multiplet. So this is a tensor multiplet. It contains a SU2 triplet of pseudo real scalars Lij. Why I call it pseudo real? Because it is not real. So what it is, like if you take Lij star, it is written as L upper ij, that is related to L lower ij in this particular form. Okay, that is why it is called real. It is not exactly, it's not real, it is pseudo real. Okay, and then you have a SU2 doublet of Majorana spinors, and you have a tensor gauge field because it's a tensor multiplet. Okay, okay, I don't, yeah, you can find the supersymmetric transformation of this also, but the action that is supersymmetric invariant is this. Okay, so where this H mu is basically the dual of the three form field strength. Okay, it's a one form. Okay, and this action is supersymmetric invariant, and now we can calculate the different components of the current multiplet that comes from this action. Okay, so the different component of the current multiplet, for example, first we'll have an energy momentum tensor arising from translation invariance, theta mu nu. You'll have a supersymmetric current arising from SUSY invariance. You will also have SU2 and U1 asymmetric currents. As I said, this will not be traceless, so the trace of this will be another non-trivial component of the current multiplet, as well as the gamma trace of the supersymmetric current will also be a non-trivial component of the current multiplet. And apart from these components of the current, so these theta mu nu, j mu I, b mu ij, and a mu, these will be conserved because these correspond to symmetries. Okay, the other components will not be conserved; they don't correspond to symmetries. Okay, apart from these components, now if you apply supersymmetry, you will find several other components of the current multiplet by simply applying supersymmetry. Okay. What we will find is that these are the other components of the current multiplet. T mu ij is essentially having the same symmetry properties as B mu ij, so it's a SU2 triplet, and it will be Hermitian or anti-Hermitian depending on how you write it. Then you will have a complex triplet of currents, and then you have a real current D, and you will have a B minus mu nu, which is anti-self dual. And you will have a current CIJKL, which will be a 5 representation of SU2. It's symmetric in IJ, K, and L. So it belongs to the 5 representation of SU2, and it will be pseudo real. Meaning, if you take its complex conjugate, it will be related to the original CIJKL by epsilons and not directly equal. And the sigma IJK is a fermion. It's in the 4 of SU2. It's symmetric in IJ and K. It's another Majorana spinor, and this is Zij is another fermion as a doublet. Okay, so these are also not conserved. So this comes by applying supersymmetry transformation on this current multiplet. So if you count the number of components, what you will find, you will get a 48 plus 48 component current multiplet. Okay, so clearly from here one can see that it's not going to give us something close to the dilaton Weyl multiplet. EIJ is a triplet of complex. It's a triplet of complex scalars. Yes.
So
yeah.
So most of this additional stuff is coming because there is a trace is non-zero, right?
The trace is non-zero. Yes.
If the trace were zero, then
yeah.
You would just get the currents and the EIJ.
Yeah. If I start from vector multiplet, probably these things and these things will be zero. I will get B minus mu nu D and is IJ. I won't get this.
EIJ would be there.
EIJ may not be there. Yeah. That's how you get standard Weyl multiplet. This will couple to T minus mu AB, and this will correspond to chi, and this will correspond to this will couple to D. But yeah, now we get all these components, and if you count the number of components, it will be 48 plus 48. So clearly there is some more additional multiplet that it will couple to. It will not couple just to the Weyl multiplet. Okay. So now along with this finding these components, you will also find the supersymmetric transformation, and I'm refraining from giving them here. It's very long, but you can find them in our paper. Then what you can do is you can couple to this linearized, let's say, so Weyl multiplet, some linearized multiplet that will couple to. So theta mu nu will couple to H mu nu, sigma will couple to some phi. This small d will couple to some calligraphic d. Oh, sorry. This auto translation. I wrote IJKL, it's made Jill. I didn't see that also. So it is CIJKL, CJIJKL, and this 1 by and B minus mu nu will couple to some T minus mu nu, and so on. So corresponding to each component of the current multiplet, you have a field. And by demanding the supersymmetry invariance of this coupling, and you know how the current multiplet transforms, you can get how the linearized field, how these fields transform under the linearized transformations. Okay, and after getting the supersymmetric transformation of the fields, if one can see that if you make this field redefinition, essentially what happens is that these components decouples from the rest of the fields and they transform like the linearized standard Weyl multiplet. Okay. Okay, so they transform like a linearized standard Weyl multiplet, and the other components where the scalar field is sitting, that transforms like a different matter multiplet, which has 24 plus 24 components, and that is what we call as the real scalar multiplet. So here the scalar field that we got from the trace of the energy momentum tensor, that is not sitting inside the Weyl multiplet as we were expecting, but it rather sits inside a different multiplet, and the other components transform as a standard Weyl multiplet. Okay, so from this current multiplet analysis, we essentially got two irreducible multiplets. So the full field multiplet was a reducible one, and it reduced into a 24 plus 24 standard Weyl multiplet and a 24 plus 24 multiplet containing a real scalar field. And
bound to happen because if you look at the current, the traceless part of the stress tensor will form one representation of the superconformal algebra, and the trace part will form the
other representation. Yeah, I mean, in the end we thought it to be like that, but it's not clear to us why it didn't happen in 5 dimensions, for example.
Yeah, so can you remind me, what didn't happen in 5 dimensions?
5 dimension, they also started from a free action of a vector multiplet,
yeah,
and constructed its current multiplet, and that actually coupled to a dilaton Weyl multiplet, and it didn't decouple actually. The current multiplets didn't decouple into these two multiplets. Yeah, but I think it's.
But in 5 dimensions, the superconformal algebra is this complicated algebra. Maybe from that side, maybe that algebra admits the traceless representation, as well as the traceless representation, one irreducible representation.
Right. Okay. Yeah. Yeah. So that's how we got. And then once you get the linearized transformation, you already know the algebra. Then you just have to apply the algebra and complete the supersymmetric transformation.
But then here you would not say that this is a supergravity multiplet, right?
This is a matter multiplet. That's why we call it as matter multiplet. It's not a gravity multiplet. Yeah. Okay. And then it has 24 plus 24 degrees of freedom. But we saw that we can actually constrain this. So usually the matter multiplets that we know in conformal supergravity are all short multiplets having 8 plus 8 degrees of freedom. Okay, the other long multiplet that we have is the chiral multiplet, which is 16 plus 16 degrees of freedom. But that can be restricted. If you know that in chiral multiplet, which has 16 plus 16 degrees of freedom, you can restrict the chiral multiplet, and you get a restricted chiral multiplet with 8 plus 8 degrees of freedom. The way you do that is that in chiral multiplet also you have something similar to Eij here. You have a Bij, and when that Bij has chiral weight 0, you can essentially restrict it to be real. I mean, the chiral multiplet doesn't require it to be a real, a pseudo-real field, but you can restrict it to be a pseudo-real field, and then supersymmetry will tell you what sort of other constraints that will imply, and in the end you will get a restricted chiral multiplet, which has 8 plus 8 degrees of freedom. So here we thought that similar things can happen, like you can have some sort of restriction imposed on Eij, but here Eij will carry a non-trivial chiral weight. It has chiral weight of -1. Okay, so you cannot restrict it to be a real field. So what you can restrict it is to be it can restrict it to be a real field up to some phase. Okay, up to some phase. So you can impose some constraint like this, where E bar Ij is basically related to its complex conjugate via this SU2 transformation. Yeah, so you can restrict it to be a real field up to a phase, where the phase will now carry the chiral weight, and then you can impose supersymmetry on this constraint to get the other constraints. And what you will find is that this 24 plus 24 multiplet will be restricted to this 8 plus 8 multiplets carrying these fields. Okay, where this is the real scalar field that was there, and this sigma is the phase that is there in Eij, and this Lij is the modulus of Eij, lambda I was already there, and this HA is the dual of some 3-form field strength. Okay, it satisfies a Bianchi identity DHA is 0 or up to fermions. Okay, and this 8+8 multiplet, can be mapped to a tensor multiplet. So the tensor multiplet can. So the thing is that the tensor multiplet, by imposing these constraints, can be embedded inside this 24+24 real scalar multiplet by taking these combinations. So this, if you take this combination, you can see that the components, these components, by taking this combination of the tensor multiplet fields, they transform like this restricted real scalar multiplets. So that was another non-trivial result that we obtained. Okay, so I will discuss in the future directions why this is important. Okay, so let me end with some future directions. Okay, so in 5 dimensions, using this dilaton Weyl multiplet, these people Oskan and Pang in this paper, they worked out all curvature square invariants in Poincare supergravity. Okay, typically, otherwise, if you follow the standard Weyl multiplet approach, which was also done by Tachikawa and Tachikawa and his collaborators in one paper, where they found the Weyl square invariant in Poincare supergravity. Okay, but using the dilaton Weyl multiplet, these people showed that you can actually construct all curvature square, like Riemann square, arbitrary combination of Riemann square, Ricci square, and Ricci scalar square.
When you say construct it, you mean open it out in components?
Yes. Yeah. So now once we have the dilaton Weyl multiplet in 4 dimensions, one can also approach to construct this all curvature square invariants directly in 4 dimensions, and also see if we can also get some dimensional reduction between the dilaton Weyl multiplet in 5 dimension and the dilaton Weyl multiplet in 4 dimension, and see how the invariants constructed in 5 dimensions goes to invariants constructed in 4 dimensions. So that is one of the future direction. However, unlike 5 dimensions, in 4 dimensions, all curvature square invariants can also be obtained using the standard Weyl multiplet by stitching together some of the known multiplets some of the known invariants that we have. For example, we already know of the Weyl square invariant in 4 dimensions. That was basically the old work by Bakshu, Deru, and Dewitt. And we also know the Gauss-Bonnet invariant that was done by Daniel Butter, David Kuzenko, and Ivano in this paper. And very recently, this a separate R-square invariant was constructed by Kuzenko and Novak. And if you combine these 3 things, you can essentially write down all curvature square invariants in 4 dimensions using standard Weyl multiplet also. So it would be interesting to see how the dilaton Weyl multiplet invariants and the standard Weyl multiplet invariants are related, and get some more insight into the relation between the dilaton and the standard Weyl multiplets in 4 dimensions. So this is these are some of the future works that we do in using the data.
Yeah. By when you say obtain the invariance, you mean open it out in components?
In components, yes.
So there's a non-trivial relationship between the various components here. The field redefinition is even in components?
Field redefinition?
What do you mean by, once you have it in components, you have it in components. What do you mean? How are they related?
Oh, no. There are these 2 different Weyl multiplets that we discussed. There's one is the standard Weyl multiplet. So they differ in terms of their auxiliary field components. The standard Weyl multiplet is the one which has this TAB, chi-i, and d. And there's a different version of the Weyl multiplet that doesn't have this TAB, chi-i, and d, but rather some different kinds of auxiliary fields.
But when you say obtain the invariant, you mean integrate out the auxiliary fields, right?
No. It's off shell. They have it's off shell. Yes.
I think you want to write the action which
Yeah.
is consistent with supersymmetry using this multiplet
And that multiplet.
Now relate
Yeah.
if these are related term by term.
Right. Yeah. So we already know how the standard Weyl multiplet fields are related to the dilaton Weyl multiplet field. So in principle, if you know the invariant constructed of the standard Weyl multiplet field, you can write down an invariant constructed out of the dilaton Weyl multiplet field. Whether these 2 are the same or they are different. If they are different, one can in principle try to invert the relation between the dilaton Weyl multiplet and the standard Weyl multiplet, which we want to see if we can actually invert the relation.
That is
Not been done.
I'm sorry for coming to late, but you write down these things as integrals of the superspace or just
Yeah.
components?
In components, yeah. Yep. I mean, Kuzenko and Novak, I think they approach, I mean, even this Gauss-Bonnet invariant also, they approach it from the superspace. But in the end, I think they write in components. Yeah. And of course, to like once we have these new invariants, you know, to understand its relevance in the context of black hole entropy, which we have seen, you know, using the Weyl invariant and yeah, if you have the all curvature squared invariants, how it affects the black hole entropy and so on can be studied. So these are the few future directions using the dilaton Weyl multiplet war. And so the
idea there is that you can try to do localization to see that.
Yes, localization. Yes, yes. Yeah, and yeah. So for the real scalar multiplet, what we would like to do is we would like to construct a density formula in terms of the real scalar multiplet. So what we know in 4-dimensional n equal to 2 conformal supergravity is a density formula in terms of the chiral multiplet. And then the whole task of constructing all these invariants is to embed all the multiplets into the chiral multiplet and put it into the density formula and obtain the actions. So now since we have this new multiplet which is a real scalar multiplet, there are some ideas of how we can construct a density formula using this real scalar multiplet. And once we know how to write out a density formula of this real scalar multiplet, we already know one of the embedding of the tensor multiplet into the real scalar multiplet. And using this embedding, we can actually write down new couplings of tensor multiplet coupled to conformal supergravity. So far what we know, the couplings of tensor multiplet to conformal supergravity is obtained by using a density formula in terms of the chiral multiplet and embedding the tensor multiplet into the chiral multiplet. So this will be a new couplings of the tensor multiplet to conformal supergravity. And why it is important? Because tensor multiplets are also used as one of the compensators to go from conformal supergravity to Poincare supergravity. So these new couplings will essentially also modify the Poincare supergravity. Yeah.
I was going to ask something related
Yeah.
to this graph.
Mm-hmm.
I mean, this real scalar supermultiplet that you obtained was obtained by considering the coupling of tensor multiplet to conformal supergravity, right? And the fact that it's not scaling there.
Yeah, yeah. Yeah, we didn't couple tensor multiplet to conformal supergravity there. We just wrote down a free tensor multiplet action and worked out its current multiplet. And then the current coupled to various components of the.
Trace, right?
Yes, it had trace.
So the trace coupled to
Yes,
this
yes.
scalar. Right?
Yes, yes, yes.
So can that scalar not be thought of as just the compensator for
It can.
for the scale
It
symmetry?
it can.
So what you ended up getting,
Yeah.
can it not be thought of as just the Poincare supergravity?
See, there are various things actually. So obviously you need some. Yeah, you need some multiplet to compensate for the additional symmetry. So usually what is done using the standard Weyl multiplet is that the compensator that you take to gauge fix the scale invariance and the E1 R symmetry invariance is the vector multiplet, because that has a complex scalar field of non-trivial Weyl and spiral weight. So using that, you basically gauge fix the scale invariance and the E1 R symmetry invariance. However, you need an extra multiplet to compensate for the SU2R symmetry and the S supersymmetry, right? So that is typically one uses either a tensor multiplet or a nonlinear multiplet or a hyper multiplet for that purpose. So here, of course, now what we have is we have a real scalar multiplet which has a scalar field with a non-trivial Weyl weight, and one can ask this question whether one can use this to compensate. I mean, one can use this multiplet directly to compensate for all the, instead of using two different multiplets, whether one can use this multiplet to directly compensate for all the symmetries of the conformal. That's also an interesting question. I mean, we also like to see that. Yeah. Okay, I think I'll end with this, and thank you.
What is the status in
6
6 dimensions?
dimensions. There is an official formulation. That I think is that old paper by Berkshire and the collaborators, where they had constructed. They also have dilaton and standard Weyl multiplet. Yeah.
You write Weyl square term there
Ah.
and write it supersymmetric completely.
Yeah.
Would the
Uh-huh.
Yeah, right.
And the Weyl anomaly will be in some Chern-Simons term, right? Will be encoded in some Chern-Simons term.
That means there are three,
Yeah,
no, yeah, three AC1 and C2
right, right.
type anomalies.
Uh, I think it will be, yeah, so I think, like for example, in 5 dimension, you have, you have a gauge gravitational Chern-Simons term that will encode the Weyl anomaly, right? I don't know if there is any asymmetry anomaly.
So this would be the anomaly of 4 dimensions.
Yeah, right.
Are you after some sort of A theorem in 6
Yeah.
dimensions?
Yeah. I mean, not necessarily 8 theorem, but just the, in 4 dimensions, we know that the A anomaly is related to the R cube anomaly. A statement like that. I think Clay and collaborators do find some version of the statement. Just a supersymmetry statement that relates the Weyl anomaly and the truth anomaly of the R symmetry.
Is there something like an A maximization in 6 dimensions?
Right, it would result, it would give you something like it.
So then that would, for the supersymmetric theory, be something like suggesting an A theorem.
Yeah. But the first step would be to make
Yeah.
the simulation.
Yeah. Has something. I suppose there's some. Is there an obvious conjecture for the theorem in 6 dimensions for a quantity that decreases?
Yeah,
The one that you get as continuation of the
yeah.
sphere free dimension. A good signature.
No, it's the A. The A that couples to, forgetting now what it couples to. Only the Euler limit.
Right. But that's the thing, that if you compute the sphere free energy and then take the
Yeah.
limit to given dimension, you get that.
Yeah.
And so if this thing obeyed a maximization in supersymmetric theory, that would be reasonable. I don't know, it would be
Yeah.
some sort of
Because of F maximization, you are saying is the A theory.
yeah, this F maximization is a conjecture, right? In all the 3 dimensions.
So you are saying that you are going to a DL theorem by rejecting R symmetry. Why are you saying this?
See, firstly, there is this quantity which is basically the sphere free energy, which in 3 dimensions we know decreases. If you take the limit to 4 dimensions, it reduces to A, which decreases. If you take the limit to 2 dimensions, it reduces to C, which decreases at that rate. So there's an actual quantity that might well just decrease in every dimension.
What do you mean limit to limit means what?
Meaning that, in 3 dimensions, the sphere free energy is a finite quantity. In 4 dimensions, it's some UV divergent quantity.
Right.
So what you have to do is just take something like, you take the sphere free energy in 4 minus epsilon dimensions.
Okay.
Now, so the first thing. Now in 4 dimensions, of course, there's a proof, this beautiful proof by Poincare. But well before that, there was reasonable evidence. And the evidence was this, that, in a supersymmetric theory, if you've got an R-symmetry current and various flavor currents, then the R-symmetry, let's say U1 R-symmetry, the various U1 flavors, the actual R-symmetry of your theory could be any linear combination.
And this F maximization gives the correct one.
A max. Yeah.
That gives the correct one. And now you are saying that because you are connecting these two R symmetries
And because you're getting the right symmetry by minimizing something, at least by extremizing something, it suggests that there is a flow, a minimization around this. Because roughly speaking, you have more symmetries in the UV than the other. So if you minimize over its limited space, you get it goes one way. Okay. So there was always this evidence for some sort of thing. Right? In 4 dimensions, I was wondering whether you want to generate evidence for this same conjecture. I mean, along the lines of what? One more, that's a great question. But what are the, is is there a computation one really wants to do using bulk localization that has not been done? I mean, suppose you had all the off-shell supergravity you wanted, what would you use it for? What would you?
Okay, so I'm not done. I'm not done this things localization, but you're asking whether there is something left to be done which has not been.
Something which off-shell supergravity is needed for that has some calculation which you could do when you had the off-shell formalism, but you can't do now because you don't have it. I remember Atish used to keep complaining that he didn't have the off-shell formalism for something.
Yes, yes. I mean, so I don't. I mean, all this I know by talking with people only. So I remember I asked this question once to Rajesh Gupta. What he told me that you don't need a full off-shell formalism to do bulk localization. What you need is at least if some supersymmetries are realized off-shell, then like you can do bulk localization and find this exact quantum entropy and all. I don't know. I mean, I'm not sure about that, but that's what that's the statement that he made.
So again, big question.
Yeah.
What about 2B supergravity in ADS5 plus S5? Is there an off-shell formalism known for that?
2B supergravity on ADS5 cross S5. That would be like
the bulk dual to N equal to 4.
bulk dual to N equal to 4 super Young Mills. Yeah. So that will be okay. ADS5 cross S5. So what supergravity will be like? It will not be the minimal supergravity, right?
I won't know the words, but I can tell you all about the field process. Right?
Yeah. I mean, the only off-shell formulation in 5 dimension is known for the minimal supergravity. There is the only off-shell formulation for 5 dimension is for the minimal supergravity. So S5 means it will have 6 SO6 arc symmetry, right? Yeah. Whereas the off-shell formulation that is known for 5 dimensional supergravity is SU2 arc symmetry. So yeah, so it will not be known for that. Yeah.
And the idea, the expectation is that there are just so many fields that nothing useful will exist, or that just remains to be found. I tell you why I'm asking. There are so many localization calculations that have been done in the field state.
Yeah.
It would be sort of nice to see if there was a topological sector of the bulk, or maybe many topological sectors of the bulk, which capture all the localization information. You might expect that you might want to try to decontaminate ADSC, in the sense that some things work just because they're exact supersymmetric things, and let's take them away and concentrate on interesting things. Okay, so if you could find like some sort of topological supersymmetric sector of the bulk which explains many matchings, and then we can see what is working because of some simpler duality and what is working because of full physical.
Yeah.
So I suppose the first step would be
to find out some off-shell formulation, or I mean. Yeah, clearly, I mean, as far as I know, there is no off-shell formulation beyond the minimal supergravity.
And this sounds like a very difficult.
Yeah. I mean, I don't know about in 5 dimensions, but in 4 dimensions, like it is for example, if you want to write an off-shell formulation for the maximal supergravity, I guess you will need an infinite number of higher spin fields in the multiplet, something like that. But I mean, even then, one can if I think about what I talked with Rajesh, like if you even if there is no full off-shell formulation, if you can find some supersymmetries which are realized off-shell, then also you can try to do localization.
No. I think one possibility is the spiral algebra, right, which exists in the plane. There should be an EDF.
Leonardo's.
Yeah. I wonder whether people have
looked at the bulk.
Yeah.
Yeah, that sounds interesting. Yeah, maybe one could find a full topological string, more than that.
Thank you.